All right, so we are here to talk about searching techniques. We're going to cover linear search. We're going to cover binary search. What is linear search? It's really the traditional searching that you've seen over an array, over a list, using a for loop, something that we have covered exhaustively. You're really going to start at index 0 and you're going to make your way down looking at every single element in that array, compare it to the key, to the value that you're looking for, see if you found it, and then you're going to return something, maybe true to indicate you found it, false otherwise. Maybe you can even return more information, such as the index, showing where you found it, a variety of options. But this is linear search, your basic way. Going from index 0, you have an array of size 100 that's completely filled with elements. We're going to search all the way down that entire array looking for a particular element in the array. Now I could just jump right to the code and show it to you, but it's worthwhile to code it up together, but we're going to do this super quick. So let's jump over to NetBeans, and I'm going to make a new project, file, new, next, and I'm going to call this searching techniques. And I'm of course, going to delete the package and the period, and here we go. And once again, it opened up at the bottom, which is super weird, but that's okay. Then you get to see how I handle that. So what I like to do is I'm just going to make an array. And in fact, I'm going to do a little cheat and look over here to my tablet where I have an array we're going to be discussing throughout this brief video. And I'm going to make that exact array. So I'm going to call it int. It's an array of integers. And I'm going to call it just ARR because I'm super creative. Equals, and instead of saying new int and giving a size, I'm actually going to create the array by giving it the explicit values I'm looking for. So 2, 6, 19, 27, 33, 37, 38, 41, and 118 is what I have on the example we're going to use. So what we'd like to do is we want to write a method that will be called linear search. It's going to return true or false. So public static boolean, and let's call it linear search. This method will return, again, I'll put return true just to get it to be quiet and stop shouting at me to get rid of the red. So it's going to return true for now, but it could return true if found or false otherwise. And what are we going to send to this method? We want to send over the actual array itself, which if you recall, well, first let me just call it, I'll call it ARR, but as you know, I can call it anything. I can call it X. It's just changing the name. It's a placeholder here, the formal parameter. So when I send over that array, and remember, something we covered previously, super important, that array is found where? We have two types of memory. We have the stack memory and we have the heap memory. The stack is where your environment is storing all of the functions, the methods, and their local variables. The heap memory is where we have that dynamically allocated storage. So when we tell Java to make me this array of this big, it's actually on the heap, and what we're doing is we're sending over the address of the beginning of that array in memory. We're sending it over to the heap, and that address gets saved right here. So what did I say we want to do? We want to do a for loop, FOR tab. We want to loop over x.length, and we want to look for a particular value. So let's say we send over the key value that we're looking for. I'll call it key. So what we want to do is we want to check if the value at index I is equal to the key we are looking for. Did I type that right? Might be good enough. So if x at index I, if it equals key, which is the value we're looking for, return true. Otherwise, we will simply go to the next index. So we're checking at index 0. Imagine the key was 12. Index 0, are you 12? Nope. Index 1, are you 12? Nope. Index 2, are you 12? Nope. So on and so forth. We check those indices. If we finally see a 12, we return true. But if we loop over the entire array and we never find anything, then after the for loop, that's very important. A common mistake is to do this right here, return false, or put an else return false. Someone might say else, and you put a return false right here. That would be a mistake. You want to only do that after the for loop. So once the for loop has finished, The comment would be, if we made it this far, we did not find the key we are looking for. Return false. This is just a review. You all are experts at this. So this here will be return false. So now we can check the functionality of this linear search method that we just wrote. So how about we can call it, and I can say, let's see, print 6 is in the array. And I'm going to print true or false. So I'm going to concatenate to that true or false, which is what's going to get returned from our method we're going to call. So I'm going to call the method linear search, and I'm going to send over array, and I'm going to send over 6, the value I'm looking for. Is 6 in this array? The answer is true. We run this, we should get true. But if I make it something that's not in the array, how about 98 is not in the array? It should be false. How about I make some other numbers so we can feel good about the solution? 37 should be true, right? I need to change the printout. I should have printed 37 is in the array, right? So you can see the number 37 down here. That is in the array. Let's do one more that's not in the array. How about 42 is not in the array, or is in the array, true or false, and this will print false. So cool, it works. And what we just coded should have looked something like this, right? Here's the array A, here's the value, and like the key. We're looking for that in the array. If we ever find it, return true, else we return false. Pretty straightforward. That's nothing new, okay? It works. What if we want to know where the value was found? Instead of just returning true or false, we'd like to return the actual index where it was found. That's actually more meaningful, right? Because if you return the index, then from the calling method, we could print something from that array. Instead of just returning true, if we return the index where we found it, we can do something more meaningful. So that's normally what you'll see happen. Instead of returning a true or a false, we'll return an index where it was found. Now, if it was not found, what would you return? Think about that. If it was not found, you might say, oh, I'll return 0. No, 0 is an index. So what would you return? You have to return an invalid index, some index that is guaranteed to be invalid, and then you can use that in your main program. So we'll return -1. If we find the value we're looking for, we're going to return the index. If we don't find it, we will return -1. So how can we edit our code? Let's make this return an integer now. If we find it, we're going to return I, the index where we found it. Otherwise, we're going to return -1. So now what can I do with this? How about we type int index found equals linear search. And we're going to, again, search in the array A. We're going to send over the reference to that array, which is on the heap. We're looking for the number 19, and it's going to return the index where 19 is found, or -1. So I can say if index found is greater or equal to 0, for example. I can do if it's -1 as well. So if it's -1, how about we do that? If it's -1, it wasn't found, right? So we can print value not found in the array. Cool, simple. Else, if it's not -1, we can print the value was found at index %d new line, and we're going to put here at index found, and I'm going to change this print line to a print f. So let's check this out now. The value was found at index 2 because we're looking for 19. What if we're looking for 38? The value was found at index 6. Is that right? 0, 1, 2, 3, 4, 5, 6. Perfect. What if we're looking for 110? So let's type in 110 right here. How about, no, more than 110. How about 150? Beyond what's in our array, the value was not found in the array, right? Pretty straightforward. Now, this -1 works because it's an index, not a value. So I can still look for the value -1, right? Or -2. Is -1 in the array? Nope, the value was not found. Pretty straightforward. And that would be a working solution. And this is something that you see here on the slide as well. How fast is that code? That's the question. If your array is unsorted, the algorithm is actually optimal. That's as fast as you can get it. The only way to be sure that an item is not found in an unsorted collection of items, worst scenario is to look over everything, right? So if I give a list of exam papers, not sorted, and I say, hey, try to find so-and-so's paper, well, you'd have to, worst scenario, look over every single exam paper. They might be all the way at the back of the stack, right? This is the idea. The question is, can we find a value in our array faster if the array is sorted? And the answer is absolutely. We can find it much faster using something called binary search. What is the idea? It really comes from this number guessing game from childhood. So I'll remind you of this silly game. I have a secret number between 1 and 100. Make a guess, and I'm going to tell you if your guess was too high or too low, and then the game continues until you find the number, right? This is what happens. And the objective is to minimize the number of guesses that you're going to make. So you tell someone, hey, guess I have a number in my mind from 1 to 100. Let's say your number is 87, and they guess 50. You say, nope, 50 is too low. They guess 60. Nope, 60. You tell them it's too low. 90. You say, nope, 90 is too high. Like, oh, dang it. 80. You tell them 80 is too low, right? You get the idea. You keep telling them too low, too high until they finally get the number 87, and you tell them, there you go, you guessed correctly. The objective of this game is to minimize the number of guesses. That's the actual objective. It's not just to get the correct answer, because if the objective was just to get the correct answer, I'd love to play this with you. And I'll say, you pick a number between 1 and 1,000. You get the number in your mind, right? You have the number ready, and I'll say, okay, you ready? Let's go. 1, you say no. 2, no. 3, no, higher. 4, higher. Obviously, the objective is not to just guess the number. I can find it eventually, sequentially guess, pulling off all numbers, right? The real objective is to minimize those number of guesses. And the first guess of most people who've played this game will be 50. Why is it 50? Pause the video. Think about, why is that first guess usually 50? And the answer is because no matter what response is given, you are at worst dividing your search space in half. That's actually what's happening. So that we're introducing this new word, search space. At worst, we have this search space. So here's an array that we're going to see momentarily. We have this huge search space right here of 100 numbers from 1, 2, 3, 4, 5, right? All the way to 50, all the way to 98, 98, 99, and 100. If you guess 70, or better, let's say 50. If you guess 50 as a first guess and someone says, yes, well, best case scenario, then you got lucky and you got it. But if they say that 50 is too high, well, what does that mean? That means that you have a guarantee that the answer, the correct number, is between 1 and 49. You have just divided this entire search space in half. You no longer have to examine numbers 50 through 100, 50, 51, all the way up to 100. Instead, we now can focus our attention strictly on the numbers 1 through 49. That's the value of selecting 50 as the first guess. Okay, moving on. So the strategy, always guess the number that is halfway between the lowest possible value in your search range and the highest possible value in your search range. So if you have some number, and if I say 50, you say too high, I'll say 25. Too high, I'll then give you 12. You say too low. So now I know it's between 13 and 24, because I already guessed 25, right? 13 and 24, it's around 12 numbers. I'll probably say 18. You say too high. So now I know it's between 13 and 17. I'll probably say 15. And you'll say, I got it. For example, this is the idea where at every step of this search, where I'm searching for your number, we divided the search space in half. And this is huge. It's called pruning the search space. Instead of searching through all 100 numbers, in fact, if we play this game, I can always be guaranteed, if I use the correct strategy, to find your number within 7 guesses. Now, if I have a calculator and I can get the exact midpoint number, if we played this same game with 1 billion numbers, from 1 to a billion, you pick a number in your mind, 1 to a billion, I can guess that number within 30 guesses. Exactly 30. As long as I choose the midpoint each and every time, only 30 guesses is what is needed. So the question is, how can we adopt or adapt this strategy when applying it to searching in an array? So we're given this following sorted array, as you see here, and we're looking, for example, for the number 19. How can we make that happen? Where is halfway in between? One guess might be, well, look at the lowest value here, 2. Look at the highest value, 18. Take their average, like 2 plus 118, 120 divided by 2 is 60. And then look for 60? But that's not even in the list, right? That makes no sense. Instead, we have 9 values. You want to look at the halfway point between them, which is right here at index 4. That's the halfway point. That's the idea. So we want to find the middle index of our current search space, which is currently, the search space is all values. So the middle index is the middle of the search space, and we want to check, hey, are you 19? Nope, I'm not 19. Where's 19? Is it lower? Is it smaller than you, or is it bigger? And they'll say 19 is smaller than me. Cool, thank you so much. Well, guess what? Now the search space is right here from index 0 up to index 3. If 19 exists in the array, it will be here because the array is sorted. And we can also ignore index 5, 6, 7, and 8 because we have just divided the search space in half, which is huge with respect to running time. So given this array, lowest index is 0, highest index is 8, the middle index is 4. The correct strategy is, hey, index 4, do you have 19? No, I don't have 19. Cool. Is 19 greater or less than the number stored at index 4? Index 4 stored 33. The answer would be less than. We're then going to look to the left. We're going to look from index 0 to index 3. And this is the overall idea. And we continue this process until we find our number or we have no more search space from which to look. Now I say here binary search code, but in fact, we're not going to do the code yet. Let's come up with the code together as we're actually understanding this a bit more. So I'm going to go back over here to our tablet. Let's actually walk through looking for this key 19 per that algorithm. So we're looking for 19, and we start out by saying, what is the search space? It's actually from index 0 all the way to index 8. What is the middle point of that search space? The answer is index 4 is the midpoint, right? So we can call this the low, this is the high, and the mid is index 4. So we're going to check the mid, and we're going to say, hey, mid, right there. Are you 19? Mid says, nope, I'm not 19. Where's 19? Or is 19 smaller than you? The answer is yes, 19 is smaller. So guess what? Instead of this whole thing being the search space, now the search space is only this part. The search space is the left side of that array, in which case we now continue and we say, okay, well, the search space is now no longer from 0 up to 8. Rather, the search space is what? It's from 0 to 3. So I'm going to simply edit this. You know what? Let me type in right here. I'm going to put low, high, and mid. So now the low is 0. The high is 3. This is the search space right here. And what's the middle point of that search space? You would say, well, it looks to be right there between those two indices. And in fact, you're right, but we need to pick one of them. So let's pick index 1 and we'll figure out later how that works mathematically. So the low is 0, the high index is 3, and the middle index is going to be either 1 or 2, and let's just say 1. And so now that we're doing that, we're going to simply look at index 1. And we're going to say, hey, yo, index 1 right here. The value you have, is that 19? Index 1 says, nope, it's not 19. So we say, okay, is 19 smaller than you? Index 1 says, nope, it's not smaller. Where's index 19? Or therefore, if you're not 19, if it's not smaller, and if it exists, it must therefore be bigger. So now the search space is what? It's this right here, only from index 2 to index 3. So I'm going to come grab the eraser, erase all of this, and I can erase those values. So now the search space is what? It's going to be from index 2 to index 3. Right here is the search space. Once again, we need to find a midpoint. We'll say, well, what's the midpoint between index 2 and 3? You'll figure out mathematically how we do this, but the answer is 2. So we're going to look right here, and we're going to say, hey, are you 19? And the answer is yes, we are 19, and we therefore exit this looping process. Now, what if we weren't looking for 19? Let's say just for kicks, we were looking for, I don't know, how about you're looking for 28? Well, if you're looking for 28, we would have said, is 28 bigger than you? We would say, yes, 28 is bigger. So now the search space would have been where? The search space would have been simply right here from index 3 to index 3. So the low would be 3, the high would be 3, the mid would be 3. And we say, are you 28? No. Is 28 smaller? No. Is 28 bigger? And you'll see what happens in just a few minutes when we go through examples of this in code. At that point, there's no more search space. We no longer have anything meaningful to look inside, and that's how we know the loop actually exits. So let's trace through another one. Let's pretend we're looking for now, instead of the key 19, let's pretend we're looking for the key, how about let's come to this side. We're looking for 41. So we start at the beginning. What is the low value? The low index is 0. What is the high index? 8. What is the mid? The mid is 4. Now I'll go ahead and show you the math. How do we get that math? I'll just write the equation. The math, let me actually erase these real quick so I can keep the equation up. The math here is as follows. Pretty simple. Search space is, to get the mid, we're going to say low plus high, in parentheses, of course, divided by 2. That's your equation. So let's look at this example now. We're looking for the key of 41. Well, let's start right at the beginning. The starting point leftmost side of this search space is index 0. The right side of that search space is index 8. 0 plus 8 divided by 2 is 4. So therefore, the mid is 4. And we're going to come right here and we're going to say, hey, index 4, are you the value 41? No. Is 41 smaller? If it were smaller, this would become the search space, but it's not smaller. So it's not smaller, so therefore we have to look over here to look for 41, which means what? When we have to look over there to look for 41, that means now the search space is from where? It's from index 5 to index 8. So the low is 5, the high is 8, 5 plus 8 is 13, 13 divided by 2, 13 divided by 2, integer division is 6 with the remainder of 1. And we only care about integer division. So you could also think of it as saying, what is 13 divided by 2, right? Just take 13 divided by 2. The answer is 6.5. We only care about the 6. Ignore the 0.5. So if we only care about the 6, that will be our midpoint, index 6. So this is going to now be your mid right here. Index 6 is our midpoint, and we say, hey, are you 41? Index 6 says, nope, I'm not 41. Well, where is 41? Is it smaller than you? Nope, it's not smaller. Well, therefore, if it exists, it must be larger between these two indices, index 7 and index 8. So let's go through that again. Let's keep tracing through this. Index 7 to 8. That is our low. Low is index 7 of the search space. High is index 8. We're right here now. And what is going to be our midpoint? Well, it's going to be 7 plus 8 divided by 2. 15 divided by 2 is going to be 7.5. We only care about the 7. So therefore, we're going to look where? At index 7, right here. And we're going to say, hey, are you 41? Yes, it's 41. Guess what? We returned true. So now as we see all of this, we've gone through it a few times, we can actually begin to try to come up with the code and to maybe, just maybe, figure this out. So I'm going to go back to our code, but you're going to see that we're going to go back and forth between the code and to this drawing, and we're going to come up with it together. So jumping right back over to NetBeans, let us make a new method called binary search. Public static int binary search. We're going to send over that array again. We're going to call it just X. And we're going to send over as well the key we are looking for. Now, what's going to happen here that's different? Think about that example. We kept looping again and again and again until we found it, or somehow we exhausted the search space. So we need to keep looping until either I'll say 1, we find the value we are looking for, or 2, we exhaust the search space. There's nowhere else to really look. So if we have to keep doing something until something happens, that's not a for loop, that's a while loop. So while something. What is that something? We'll figure it out. Let's call it while true for now. What are we going to do at every single step of the iteration? Let's in fact come back over here to the tab. At every step of the iteration, well, we had a low, right at the beginning, we had a low, which was 0. High was that last index of the array, which is 8. So high was 8. And then that's how we started. And then at every step of the iteration, we calculated. First step was calculate mid. And then second step was check if the value is at mid, if it's smaller, or if it is greater. So we calculate our mid and so on. So how can we now make that happen in code? Well, before we need to even enter this loop, we need to make some variables. We have to have int low initialized to 0, int high initialized to the last index of the array. So this would be x.length minus 1. That would be index 8 when it's length 9. And then we will also have an int mid. So here, what are we going to do? Step 1, calculate mid. What was mid? Mid was low plus high divided by 2. Cool. Step 2, look for key at index mid. So if x at index mid is the key, we are done. Return, instead of returning true, return the index where we found it, which is what? Return mid. But if now it doesn't equal the key, remember if we come back over here to the tablet, if we're looking for, let's pretend we're looking for 19. So erasing all of this, we don't need this, this, and this. We're looking for not 41, but instead we're looking for 19. Low is 0, high is 8, mid is 4. We say, are you 19? Nope. Is 19 smaller than you? The answer is yes. And let's see what happens. Let's first answer that. Is 19 smaller than you? How do you make that happen in code, right? So is the key smaller than the index we are at? Or I say, is the index, or you could say, is the index you are at greater than the key? But I'm going to start with the key. So in which case, let me reverse this. Same logic, or same meaning in code, but I want to reverse it. Does the key equal the value at the mid? Return mid. Is the key smaller than the index we are looking at? If the answer is true, so if the key is smaller than x at index mid, What do? This is important now. What did we do actually if you come over here? If the key 19 is smaller than 33, what did we do? Well, this became the search space right there from index 0 to 3. So what effectively happened? Well, what happened is we updated our high. The high, instead of being from 0 up to 8, now the search space is from 0 to 3. So what effectively happened is we updated our high. That's what happens under the hood in the code. If the key is smaller than the mid, we say high is now going to be equal to what? And on this example, high was equal to 3. Well, how can we represent that more generally? Instead of just saying equal to 3, we could say high was equal to the mid, which was 4, minus 1. That's the idea. So we can say that high equals mid minus 1. Update high. And then, oh, that should be an else if, by the way, right here. This is else if. And then finally, we have else. What do we do here is we're effectively going to update our low. But let's just trace through that example. Let me erase all of this. Here, if we were looking not for 19, but we're looking for instead, how about again, we're looking for 41. And so our low is 0, the high is 8, the mid is 4. Are you 41? No. What's going to happen is now, as a result, the search space is going to be this right here, from index 5 to index 8. So what gets updated? Are we updating the high? No, the high is still going to be 8. We're updating the low. The low is no longer going to be 0, right? Now the low is going to be right here, index 5. So how can you make that update in a very general sense? We say, oh, well, now low is going to be 1 more than the previous mid value, which is index 4. So in the code, when we update our low, we're just going to say, you know what? Low equals mid plus 1. That's your code. It's really that simple. There's only one tiny thing left, and that is this. Because right now, it's going to keep running indefinitely if we run out of search space and we don't find the item. But let's first go ahead and test this. So if index found is -1, we want to do, instead of linear search, let's do binary search now. Binary search. And we're searching for the value 19. We run this code. The value was found at index 2, which is correct. If I now look for the number 41, we search for 41, and we see here that 41 was found at index 7. That is correct, but get ready. If I'm looking for the value 120, it's just going to keep running and running and running and running and running, because I didn't say when to stop if it's not found. So what actually happens is the following. It's easier with some hand motions, is that the beginning, the search space was 0 to 8. Let's say that this was going to be your low and this was going to be your high over here. And so we go to index 4, which is right in the middle. And let's say the answer was no, it's smaller than 4. So we divided the search space in half. So now we're looking at just this search space from 0 to 3. Where do we go? Index 1. So now the search space is here. Well, from 0 to 3, index 1 is mid, and it's bigger, so we come this way. We keep basically, what happens is the search space is divided in half, divided in half, divided in half, divided in half. Well, if you never find the item, what happens is the search space will become 0. In fact, when you follow this code through to its end, what will actually happen is low will no longer be less than high. And one of them will get updated, and therefore you come to a conclusion that the search space, how do we know when we have a search space? Because really a good comment would be continue looping or keep looping as long as we have search space available. right? If there's no search space, if it's 0, you don't want to keep looping, right? So as long as we have search space, keep looping. How do you translate that to code? Encourage you. Pause the video, see how you would try to translate that to code. And the answer is you just say while low is less than or equal to high. As long as low is less than high or even equal to high, because if they're both equal, the same index, there's still one more value in the search space to look at. As long as low is less than or equal to high, we can keep on searching. And this is now binary search, but what did it not like here? I must have hit something funky. Let me hit save. Where's there an error? Of course. So here, if we break out of the loop and we never found it, so if we make it until here, that means we never returned. And the value was not found, return -1. That's the idea. We have to put that return -1 right here. And so now when I run the code, of course, 120 returns a -1, and it was not found in the array. So coming back over, we have our binary search code. That's with true and false. Better, as we've already shown, return an index or return -1, and this is what we get. What is the efficiency of binary search? This is what we want to end with. How fast is binary search? At the end of each iteration, all we do is we really update low or we update high. That's all that happens. And this modifies our search space, essentially having it at each iteration. So let's do an analysis. How many comparisons are necessary when running this algorithm on n items? So let's try it with a specific number, the value n equals 100. If the array size is 100, after one guess, we have reduced the search space from 100 values to 50 values. After two guesses, the search space gets reduced to 25 items left. After three guesses, it becomes 12 items left. Four guesses, 6 items left. 5, 3 items left. After 6 guesses, we have 1 item left, and we can make one more guess. It may be right or it may be wrong, because maybe the value is not found. So it really takes, with 100 items, 7 guesses, and we can find the value guaranteed. In a more general case, when we have an array of n items, not 100 items, but n items, after one guess, we have half of those items left, so n over 2 items left. After 2 guesses, we have n over 4 items left. After 3 guesses, we have n over 8 items left. After 4 guesses, n over 16. 5 guesses, we have n over 32. You keep going. After 6 guesses, n over 64 items left. Okay, well, we can say in a very general sense, after k guesses, we have n over 2 to the k items left. And how did I come up with that? Well, if you back up to this after 4 guesses, we have n over 16. All of you were probably agreeing with me, right? Well, 16 is really just 2 to the 4. Or after 3 guesses, we had n over 8 items left, right? Well, what is 8? It's 2 raised to the 3rd power. So we were able to actually see the guess number, which is guess number 3, right here within this denominator. Instead of saying 8, this is really 2 to the 3rd. Or 4 guesses, we have n over 2 to the 4 items left. After 5 guesses, we have n over 32 items left, which is n over 2 to the 5 items left. I'll do one more. After 30 guesses, we have n over 2 to the 30 items left, which means after k guesses, we have n over 2 to the k items left. What the hell is he talking about? What's the point? Well, we want to be able to figure out how many guesses are required for us to find the item. So what we've come up with is after k guesses, we have n over 2 to the k items left. The question is, how many k guesses need to be made in order to find our answer? That's the purpose of this entire last slide, building up to this final bullet point and saying that how many of those k guesses need to be made. When n was 100, the number of guesses that needed to be made was just 7. When we got to 7, there was one item left, period. If n is, as I said, a billion, you only need 30 guesses. Well, how can we prove that mathematically? What's going on here? We have this general idea after k guesses, we have n over 2 to the k items left. The question, how many k guesses are required in order to find our answer? What is k, right? This is the idea. When we want to keep guessing till we have one item left, which is either our answer or we're done. So this is the idea. So what we want to do is we want to set this equal to 1 and then solve for k, because we want to keep guessing, right, until there's only one item left. And we know that after k guesses, we have this many items. Well, we want to keep going till there's only one item left. Solve that for k. Do we remember, this is actually pre-algebra. Of course, we know that we can multiply both sides by 2 to the k. Let me actually come over here to the tablet. And so we come over, we have n over 2 to the k equals 1. As we know, I can multiply both sides by 2 to the k, the value of which, what happens? This cancels with this, and now I have n equals 2 to the k. Here's where most probably forgot some basic pre-calculus, and that's okay. But if you want to solve, let me write this clearer right here, n over 2 to the k. If we want to solve for this value, how do we get that value to come down? Just as a reminder, if I had, for example, let's say 17 raised to the x power, and I want to get this x down, I want to solve for x, what can you do? If you actually take log base 17 of 17 raised to the x power, so if you had this right here, you had this right here, but we take log base 17 of that, what happens is all of this basically goes away and the x comes down on its own. This is the idea. So here, when I have n equals 2 raised to the k, what can I do mathematically is, well, if I take on the right side of this equality, if I say let's take the log base 2 of 2 to the k, but whatever you do to one side, you must do to the other side. So I have an n over here. Well, I need to take the log base 2 of n. Well, this cancels with that, and so we're left with that k equals log base 2 of n. And if you didn't remember that mathematically, that is okay. This is not a math course. But moving on, what we're left with is when we solve this, n equals 2 to the k equals log 2 of n. This means that binary search takes log base 2 of n comparisons on an array of size n items. What does that mean to you? Well, consider this chart to see how fast log is and how fast binary search is. So if n was 1 billion items, consider if you didn't know binary search and you had to use linear search over an array of 1 billion items, looking over literally all of them, index 0, index 1, index 2, all the way to the end. How exhaustive. But if that array is sorted, and if you know binary search, you have a guarantee that you will have, because log of this number, which is larger than a billion, so log of a billion is actually a little bit smaller than 30, but log of this number base 2 is actually 30. In 30 guesses, you have a guarantee to find that item. Be impressed with how fast binary search is. This is an epiphany of how fast it is. Imagine if you had to search everywhere with linear search. What a disaster, and how slow we'd be asking Google for answers, and it would be taking forever looking through trillions of records, right, that have been indexed. And instead, we have much faster searching algorithms. Binary search is huge. We're done. The takeaway here, you need to know the speed. What's the speed of linear search? It's O of n. We haven't talked about what O means. We'll get to that later. Just know it's n. Or you want to say it perfectly or correctly, say O of n. What's the running time of binary search on a sorted array? The answer is O of log n. Again, what is this O? I'll even write it down for clarity, but it's actually, you would say the running time of binary search is, I'll write it in red, O of log of n. And we're going to talk about in a few weeks, what do we mean by this O? It comes from Big O. Feel free to look it up if you like, but we will go over that in a bit. That is it. Of course, we have to end here with our daily demotivator. And I realized that in the last set of slides, I didn't give much of a background. So you're like, what the hell is this? So some background. I went to college in the 90s. At this time, the success posters were the thing. Every single business had success pictures throughout their building, right? They were all the rage, made famous from this one company in malls. Every mall had it, called Successories. So you have these posters. I'll display two right here. Dare to soar, teamwork, winners. You have all these great posters, and honestly, I bought a lot of them. I bought posters. I bought, the swag, the mugs that said, I don't know, success. It was all the rage. And I love dry humor as well. So despair.com, they use dry humor and satire to create some absolutely incredible posters. Please, you can ignore the end of these videos, but I'm going to show one each time. I think they're comical. And actually, you'll see one in one of our offices as well. These posters, they fully resemble the one from Successories. Of course, the message is completely different. So each set of slides has one such poster. And here is our demotivator for today. Limitations. What would the real one say? If you spread your wings, only then will you know how far you can fly, right? Something like that. Here it's limitations. Until you spread your wings, you'll have no idea how far you can walk. These are so horrible. It has been a lot of fun. As always, reach out, ask any questions if you have any. Take care, everyone.